potential step, and it is continuation of the last lecture in which we looked at some large amplitude controlled potential techniques, of which the potential step is an important part, and we looked into some of the initial details of this topic. Now in this lecture we will see that what is a potential step and what are the different parameters which are related to this important concept. So to start with, let us look at this diagram which give a generalized excitation signal for potential step technique. So what we see over here is, the first thing is that there is an initial potential. Actually this axis, which is the y-axis, is recording the potential and it is plotted versus time over here. So what we are recording is the potential versus time. So initially we have this potential, which is the initial potential over here, and this initial potential is remains same from here to here. Let's say that it is actually working on an electrode. So what we see is that after it reach here, then it immediately go from EI to ES, which is this part over here. So what does it mean? That the potential which was initially there is instantly stepped to a new potential value, which is ES. This is the step potential. Now we see that this potential which is attained, this remains same from here to here. That is, it is not changing, and during this period the duration is called tau. So tau actually give us the time in which this step potential remains same. Now afterwards this step potential is instantly decreased to another value EF, which is a little lower than the EI. That is, it is a bit lower than the EI. So when it is lower than the EI, then we are actually getting to a new value EF, which is the final potential. So this is how the step is working. So you can see that first it is same, then it is instantly going to another value which is ES, and then it remains same for a period of time, and then it is instantly decreased to another value, and then again it remains same. Now let us consider what we saw earlier, that is, we consider the reaction again, that is the heterogeneous electron transfer reaction, in which the oxidized species take up an electron and transfer, and it is converted into a reduced species. So this is an equilibrium over here, and obviously during this reaction one species, that is the oxidized species, is taking up electron and it is converted into another species which is R. Now we know that this oxidized species is present at some position. So if you remember from the last lecture, then this oxidized species, if we say that this is the electrode and this part here is the solution, then this oxidized species is present in bulk, that is in solution, because it is soluble, and then it is also present, especially if there is a double layer formation in this area. Let's say there is a double layer, then this oxidized species is also present over here. So initially we say that there is no reduced species present. R is equal to 0, or concentration of R is equal to 0, and all the concentration we have is the concentration of the oxidized species, which is equal, or say nearly equal, at the interface of the solution and the electrode and inside the bulk of the solution. So initially this is the situation when this potential is applied. So as soon as this potential is applied, that is, it is stepped up, then this oxidized species is taking up electron, and we say that here this species R will be produced, and it will remain so, that is, it will be produced up to this point, and obviously it means that the concentration of the species R is increasing during this time, and then afterwards this step potential is suddenly decreased, that is, it is stepped back to a final value. And let's say that if this potential is positive enough, then it would mean that this species R will be converted back into the oxidized species. Now you can imagine that we are talking about this equilibrium over here, and when the equilibrium is present, it means that it will involve the Nernst equation. So we will see some details afterwards. I hope that you understand that what we are going to, or what we are about to see further. So potential step, tau is, that is, the step time is usually determined by the type of information that the experimenter desire of the particular system. So it means that this step time that we earlier saw, that is this time between over here, that is when it was increased and then it was decreased back. So the time it remained stable, that is, it remained ES. This is the step time. So this tau is usually determined by the type of information that the experimenter desire of a particular system. So it means that tau may vary as little as 10 microsecond to as long as several seconds, depending on the type of information. So the tau minimum is limited by the ability of the potential state to charge the electrode, and tau maximum is determined by the onset of the convection from vibration or density gradient. So initially we considered few things, that is, we saw that we are talking about in this type of processes, we are talking about diffusion. So I need to erase that first, that is, we are talking about diffusion controlled reactions. You already know that what was diffusion control. Diffusion control was there because we are talking about the double layers, and once the potential is stepped, then the reaction which is taking place will be depending upon the oxidized species diffusing into the electrode solution interface, where the oxidized species is reduced to the species, that is, to the species reduced species R. Now again, so tau maximum is determined by the onset of convection. So once the process is no longer diffusion controlled but convection become involved, it means that it has reached a maximum time. Now to avoid this, there are sometimes special shielded electrode that enables time of the order of 100 seconds to be reached with no disturbance of the diffusional process. That is, the diffusion will continue, it will remain a diffusion control process, and it will avoid any perturbation from convection or from vibration or other density gradients. Now the other thing is, the potential step ES is generally terminated by switching the potential to some final value EF, as we saw, and at this EF the reduced species R will be oxidized back to O. For that purpose, this value of EF need to be positive, sufficiently positive. So if it is positive, the concentration of R at electrode surface can be essentially or made zero. Now the result of this is that the accumulated R will now diffuse to the electrode, where it is consumed by oxidation back to the oxidized species, the original species which was present in the solution. So initially we know that initially only O is present. So this is one point. So once we step up the potential to ES, that is in an instant, then ES will lead to the formation of R. So once R is produced, it means that now this type of equilibrium may exist. Now this R, when EF, that is the final potential, is applied to R, this R convert back to oxidized species. But the thing is, before this EF is applied, that is, if you remember this region, so EF is a little bit low, so if this is the potential, then let's say this is potential E, and then this is basically the time over here. So once this EF, this is, let's say, EI, and this one is EF. So EF is a little more positive. So once this EF is applied, before that we have this much of time, which is tau, and this value over here is ES. So at ES, during this time, this R was produced, and basically this means that R was building up over here. So this R build up is actually consumed by oxidation back to R, to the original species. Now what happens if this R have some solubility in the electrode itself? Obviously this will actually turn up into another situation. So here is the situation that we are talking about, that potential which is stepped from ES to EF at 10 millisecond, that oxidation of R is now diffusion control. R to O is now diffusion control, because R is having, due to this lag over here, R was built up and its concentration is high at the electrode solution interface. So it is high due to that reason the R can diffuse into the electrode. This is electrode, we already know, and this one over here is electrode solution, electrode solution interface. So this is electrode solution interface. So what is happening, that as the time passes, some of the R goes into the electrode, and this is why that at longer times, that is at 11, 15 and 20 milliseconds after step to ES, R is soluble in the electrode and it is penetrating into the electrode, and which will be present inside the electrode and will be converted to oxidized species over there. That is, this reaction will be taking place inside the electrode. So this is the part of the figure that we saw earlier but didn't discuss it in detail. So here is the detail. Now potential step, the exact ratio of O and R concentration at the electrode surface is related to the imposed potential by the Nernst equation for a reversible couple. The The reversible couple is already known. This is O plus N E goes to R. Again, this is an equilibrium. And now what we are looking for the concentration of the reduced species at the surface of electrode and concentration of oxidized species at the surface of electrode. We already know the meaning of this is the applied potential, and this potential is also from the previous lecture. You can look for it. And then what happens, since this is a reversible couple, so if we impose the diffusion control conversion of oxidized species to R as described earlier, the potential E which is impressed across the electrode solution interface must have a value such that this value, which is C, that is the ratio of the reduced species at the surface to the ratio of the oxidized species at the surface, should be large. That is, as the time passes, more of the reduced species will be accumulated and almost no oxidized species will be present if the potential is stepped to a certain value of ES. So how much large it should be to ensure that the concentration of the reduced species is very much high and the concentration of the oxidized species almost approach to a very low value, or say to a negligible value. So let's see. So here is the table. We can see that for that to happen, we are looking for this ratio. That is, for one electron system, when minus 177 millivolts of current is applied, then we have this ratio which is 1000 to 1, and this is considered as if the concentration of the oxidized species is 0 at the electrode solution interface, or say on the surface of the electrode. So what does it mean? I have to remind you that it means that all of the species which is present over there, that is the oxidized species, is immediately converted into reduced species. Similarly, for two electron system, minus 88.5 millivolts will suffice. So this is only applicable to a reversible system. And similarly, if you want to do the reverse process, that is to convert the reduced species into oxidized species, then you will be looking for this kind of voltage. So what you have to do is to identify the potential steps in different real-time studies, and then you have to check for various parameters on the same figures from different studies. What is present on the x-axis, what is present on the y-axis. For example, if we consider our previous lecture, we see certain example like this one. So this is the example of the chronopotentiometry, that is in a single step. We see that here is the initial potential and it is instantly step up, and it remains so during this time. What is happening, we can see that over here, that is, this is the concentration which is initially present, and it is reducing or falling at the electrode solution interface, while the concentration of the reduced species is high at the electrode solution interface, but it also falls with time, but not at the same pace as the concentration of the oxidized species. But obviously the concentration of the reduced species is low into the electrode but high at the electrode solution interface or at the surface of the electrode. Similarly, if you look for the same for a double step process, you note that first it is initial potential, then it is increased, then it remains the same, during which the reduced Pc is piled up on the electrode surface, and then it is falling down in an instant to the final potential, and after that it remains same. And you can see that the response that we get over here is different when compared to the previous slides. So here I will end my lecture, and I hope that you will actually look for similar results in different research articles which will help you to understand this phenomenon.